You know, the perfect circle, the arc of a thrown ball, even the orbit of the planets. What if I told you they all come from the exact same hidden place? It's true. They're all secret shapes just waiting to be found inside one simple object, the cone. So let's get into it. So here's what we're going to do. First, we'll build a proper mathematical cone. Then, we'll get out our virtual knife, a plane, to discover its 4 hidden shapes. And finally, we'll see how these ancient curves are still to this day shaping our world. So, when you hear the word cone, you're probably thinking of an ice cream cone, right? Or maybe a birthday hat. And that's a perfect place to start. But the cone we're talking about, well, it's a bit grander, a bit more infinite. Let's build it. Which brings us to a pretty wild question, right? How can a simple party hat and the path a planet takes through space have anything in common? It seems impossible, but the answer is all in the geometry. Okay, so picture this with me in 3D. First, you've got a straight vertical line. Let's call that the axis. Now bring in a second line, we'll call it the generator, and have it cross the axis at just one single point. That's the vertex. You with me? Okay, because here's where the magic starts. We're going to take that generator line and spin it, rotate it all the way around the axis, but keep that vertex point locked right in place. And as it spins, it starts to trace this incredible shape. And this is what you get, a perfect double cone. It looks like a kind of infinite hourglass, right? It's got a top half and a bottom half, and in geometry, we call those halves nappies. This amazing 3D shape, this is the treasure chest that holds all the shapes we're looking for. All right, now for the really fun part. We're going to take a perfectly flat sheet, mathematicians call it a plane, and we're going to use it like a knife to slice right through our cone. And here's the secret. The different shapes we find, they don't come from changing the cone. It's all about changing the angle of our slice. Okay, so this is absolutely crucial. We've got 2 angles to think about. First, there's alpha. That's the angle of the cone itself, basically how steep its sides are. That angle is locked in. It doesn't change. Then you have beta. That's the angle of our slicing plane. Think of it as our angle of attack. Beta is the one we get to play with, and by changing just that one angle, we change everything. All right, let's start with the easy ones. We'll make some nice, gentle slices first. These are going to give us our 2 closed curves. You know, the ones that actually loop back and connect to themselves? So, first up, what happens if our slice is perfectly flat, like completely level? We bring our plane in so it hits the cone at a perfect right angle to that central axis. So our angle, beta, is exactly 90 degrees. And what do we get? A perfect circle. It's a clean, simple, totally symmetrical slice right through one of the nappies. Pretty simple, right? Okay, but now things get really interesting with just a tiny little tweak. Let's take that same flat plane and just tilt it, just a little bit. The key is that the angle of our slice, beta, is still bigger than the cone's angle, alpha, but it's less than that perfect 90 degrees we used for the circle. And just that one small change gives us something brand new. Our slice isn't a perfect circle anymore. It's an ellipse. You can basically think of it as a stretched out or kind of squashed circle. And notice, we're still only slicing through 1/2 of that double cone. And that's the key thing to remember about these first 2 shapes. For both the circle and the ellipse, our plane only cuts through one nappy, either the top or the bottom, but never both at the same time. They're complete, contained shapes. Okay, let's keep going. Now we're going to get a little more dramatic with our slices. We're about to make some curves that are open. What does that mean? It means they don't loop back around. They just shoot off into infinity. This next one is all about precision. You have to get it just right. We're going to tilt our plane until its angle, beta, is the exact same as the cone's angle, alpha. So what that means is our slice is now perfectly parallel to the side of the cone. And when you nail that perfect alignment, you get this, the parabola. It's that classic U shape. And unlike the circle or the ellipse, this guy is never, ever going to close. Its arms just keep going on and on forever. But look, it's still contained inside just one nappy. All right, time for our last shape. And for this one, we're making our most extreme slice yet. We're tilting the plane even more, so much that the slice becomes super steep. So steep that its angle, beta, is now smaller than the cone's angle, alpha. Think about that. We're slicing at a steeper angle than the wall of the cone itself. And because we're coming in that steep, something totally new happens. For the first and only time, our plane isn't just going to cut through one nappy, it's going to slice through both. And that gives us our final shape, the hyperbola. It's unique because it's not actually one curve, it's two separate, perfectly mirrored branches. And just like the parabola, they're infinite. They just race away from each other forever. This is the only conic section that comes from slicing both halves of the cone. Okay, so we've sliced up this imaginary cone and found four kind of abstract shapes. So what, right? Well, here's the amazing part. These aren't just doodles in a math textbook. They are literally the blueprints for how our universe works. Let's put it all together. That perfectly flat slice, that gives us the circle, the basis for pretty much every gear and wheel ever made. We tilt it just a bit and we get the ellipse, the path planets take around the sun. We line up our slice perfectly with the cone's side and boom, the parabola. That's the path of a baseball after you throw it. And that last, super steep slice that cuts through both halves, that's the hyperbola, the exact shape a jet creates when it breaks the sound barrier. And it's their unique properties that make them so useful. An ellipse has these two special focal points that are perfect for designing things like car headlights to focus a beam of light. A parabola is amazing at gathering up signals and focusing them on one spot, which is exactly what a satellite dish does. Even the hyperbola is used for things like navigation systems. These shapes are everywhere, and they are doing some serious work. So, that's where we land. All of this incredible complexity, planetary orbits, the flight of a ball, even sonic booms, it all came from one incredibly simple idea, slicing a cone. It really makes you think, doesn't it? If one simple 3D shape can hold all of these fundamental curves, what other beautifully simple rules are out there, just hiding in plain sight, governing our entire complex world?